yesterday, we have a delta V, which is the change of velocity we realize with our rocket, which is given by a first step that we call as our propulsion delta V.
Professore, mi scusi, noi non vediamo la lavagna.
Sì, si sente pure abbastanza male.
Sembra facile, eh? Allora, adesso vedete la lavagna. Sentite sempre male? Prima qualcuno aveva detto che sentiva bene, adesso sentite male?
Sì, c'è un rumore di sottofondo, di interferenza.
Il rumore lo sentiamo anche qui. C'è un rumore a bassa frequenza, lo sentiamo anche qui. Però così ho le mani libere, non c'ho il cellulare come ieri, quindi dovrebbe essere meglio. Penso che sul rumore non possiamo fare molto. So this is where we were yesterday. Now you see the whiteboard, and we can consider that we had some losses. So it means that the delta V we realize is less of what provides in theory our propulsion system. Or in other words, we have to provide in our propulsion system something more than what would say the short-cut equation. And these losses are due to, let's say, in this basic overview, are related to steering, drag, and gravity. So we non facciamo più lezione.
Però sulla lavagna non si vede neanche adesso.
Sì, va bene, adesso facciamo di vedere. Che qui si vede, è interessante che qui si vede. Passo forte, vivo al fermo, ed è questa quindi. La telecamera del computer che non c'è perché non noto perché la telecamera è quella e non funziona. Now you see something. Vedete qualcosa? Vedete qualcosa?
Sì, professore, adesso si vede.
Spero che sia leggibile, forse un po' più piccola di quello che si può. So what we saw yesterday about the drag losses is that they are more important when we have small launchers compared to big launchers, because we have that the different role of the drag, which is proportional to cross-sectional area, and the mass, which is proportional to the whole volume of the rocket. And so we should try to have thin rockets if we are considering thin and high rockets and tall rockets, or blunt rockets if you have big masses. If you have small rockets, we have typically something different.
Professore, scusi, potrebbe parlare un po' più forte perché il rumore cioè non si sente niente.
Ok, parlerò col microfono in mano così mi sentite e non ci sarà, sperando che sia l'ultima, perché se no passo alla tavoletta, chiudiamo tutto, me ne vado al mio studio e faccio lezione da lì. E finiamo con le lezioni in presenza, perché se questo è il trend, ma va bene. Allora, vediamo di riuscire a finire un discorso. I was talking about the drag losses, and drag losses are more important when we have small rockets. This is what we have seen yesterday. Today, I would like to focus a little bit more on gravity losses. Gravity losses are related to, let's say, to a term that we have seen as the integral along the burning time. Can you hear now?
Sì, ora meglio, grazie.
Also try to raise the volume of your computer. Anyway, we see the sine theta dt. So we can take an average value of this quantity and see that we have two important things. One is the angle. If we have that this theta, which is the angle made by the velocity direction with the horizontal direction, so if this theta is equal to 0, we expect that we have no gravity losses. On the other hand, if this theta is 90 degrees, so we are considering vertical flight, we have this sine theta is equal to 1, and so we have the maximum gravity loss. So this term asks us to move in direction perpendicular to gravity force, and if we have that in some phase of the flight we have an angle theta, this time t will be the time more or less when we have that this theta is not 0. That means that we should minimize this time to reduce at maximum gravity losses. So we we see that we have two opposite requirements between drag and gravity losses. In both cases, we should minimize time, but in one case, for the drag, we should move outside of the atmosphere in the shortest time as possible. So this means to fly vertically, whereas for the gravity losses, we should fly horizontally. In fact, if we are considering a launcher, we should have low velocity within the atmosphere, and this is something that doesn't fit well with a short time, because we are d squared. That means in this term that we have seen yesterday, the drag losses are proportional to 1/2 rho d squared m a b c b average value. So of course we should reduce this time, but of course this is not possible if you have small value of velocity. So there is this, of course, this opposite effect, and also we have mentioned for the fact that you should have small values of t and possibly theta equal to 0 for the gravity velocity. So as we are talking about time, here we have a role also of the thrust level. So time is related to the thrust level, because the acceleration will be related to the amount of thrust I'm getting with this rocket. So let's see this in this way. Up to this moment, what we have seen is that performance, or let's say our goal, we said we have delta V, we have some epsilon, that is the inert mass ratio that characterizes our rocket. We try to get the maximum lambda, and our rocket is characterized by given specific impulse and, let's say, inert mass ratio. So we have delta V is the requirement, lambda is our goal, that we have to improve as much as possible, and have that our rocket is characterized by given specific impulse and inert mass ratio. There is no thrust, no time in this equation, in this rocket equation. So at this point, once we examine the trajectory, we mentioned these losses, time starts to play a role. And so if time plays a role, it means that it's also important how much time we need to reach a given velocity, and this is made by the thrust level. The thrust level not only decided in a certain sense acts on the time that results for getting a given maneuver, but also on the acceleration, because if we have to change the velocity in a short time, it means that we need a high thrust, and we do this by a strong acceleration. So this means that with thrust, we play a role on the acceleration we realize with this rocket. And we have, at the beginning, we have a given mass, m0, we have a given thrust level, and as a consequence, a given acceleration level. At the end of operation, we should consider that the acceleration, we have to think something here. Let's make better. We see that we have also final acceleration, and in principle, it may be different than the first one. AF can be different from A0, and even if we consider a constant thrust, because we are changing the mass of the rocket. And in fact, if we consider the case with constant thrust, called thrust is T. So constant mass flow rate, we can get rocket with such property. And if we consider that the source velocity, effective source velocity of specific impulse is not changing much, we can say that our thrust is more or less constant. If this is true, we have that between the A0 and AS, we consider this ratio, of course it will be exactly ms over m0, and this is our mass ratio. So if you have to get a high delta V, that means that it needs a small value of mr, or mass ratio, it means also that we have a small ratio between the initial and final acceleration. So if you should lift off from ground, so that you have that initial acceleration should be greater than 1, if this is true, you can see also written on this way. If we have realized the Km of 10, it means that the final acceleration is 10 times the acceleration we have at the beginning. That is not convenient. It's not something that we can accept easily. So we can also make in this expression appear or relate the burning time to this acceleration level, just recasting the equation and assuming that we have a constant mass flow rate expressed as the rate of the propellant mass over the burning time. So if we compare these two equations, I can say that Pb is equal to mp over dot mp, and dot mp we have divided by the specific impulse. This is like the expression we have seen for the total impulse. It's an F. So mp raised to divided by m. And if we compare this with the expression of the acceleration, we see that here, if we recall theta is mc over m0, the propellant mass fraction, we can express our time as v m0 specific impulse over s, and s over m0 is just a0, or theta 13 seconds divided by how many times the, or let's say, the initial acceleration in terms of G0. So you see that there is a direct relation between the time, the burning time, and the acceleration level. And this can be also seen in terms of the final acceleration. And in this case, we should of course exploit also the mass ratio, and then we also recall that there is a relation between the mass ratio and the propellant mass fraction, which is 1 minus. So what we do with this, of course, mass ratio means also our related to delta V and specific impulse. So we can say now plot where we have our delta V over the specific impulse as a function of the propellant mass fraction, and we can now see here the effect of gravity losses, because we have seen that our T is related to gravity losses are related to our TB, and TB is related to the acceleration with the expression we have just seen. So if I now consider my delta V plus term related to gravity losses, and if I assume that TB of this expression, I can make substitution and see this kind of plot, because I have that here. This is 1 minus z, it's minus in front of logarithm, and I can express delta V over UEQ is equal to minus logarithm of 1 minus z. I'm dividing everything by UEQ, and UEQ appears here, so we have minus G yes, this is delta V. V over AG. That's by substitution, and this is our propulsion. So if we assume that this is more or less 0, we can see that here we can consider first curve on this diagram relative to the case when we have the minimum for liftoff, which is h0 over d0 equal to 1. So we have just the force to liftoff. We have a force at track which is equal to weight of the vehicle, a liftoff that is minimum to liftoff. So in this case we have a line like this. We have theta equal to 1, and we can say that we have this part, the the upper part of the diagram is allowable, and the lower part is not. So here we have no lift-off. And this is corresponding to A0 equal to 50. If we increase the thrust level, the initial thrust, the thrust level in general means that we have that this A0 is greater than Z0, and in this case we realize curves which are on top of this other one, because we see that if we increase this, we reduce the subtractive term, and so we have other lines up to this one, A0 over Z0 infinity. So this is just the final line is our, let's say, propulsive delta V. Because we have, if this becomes so large that this term is negligible, we have eliminated the very velocity by this equation. So you see that for a given value of V, we have that in general this difference is our direct velocity. Because it's the difference between what we would obtain ideally, this delta V, and what we obtain in the real case. In this case, with respect to the condition where we have our minimum for lift-off. But we have to consider also the maximum acceleration, because especially if we move towards high propellant mass fraction, there will be a multiplier for the acceleration starting from the initial one that will be greater and greater as we have seen that is actually proportional to the mass station. So we can see that the same expression can be obtained also in terms of final acceleration, considering that A0 is equal to AF mr or AF 1 minus 3 and we substitute here A0 and it becomes delta V over UE equal to minus logarithm 1 minus V minus G0 G1 minus G1 over AF. And yes, everything. So we can see that we can consider different values of AF over G0 on this plot. And we have lines that are of different shape, because there is 1 minus 3 also that tell us that we have very high acceleration, and these lines correspond, for instance, to AF over G0 equal to 2, 4, 6. Of course, we are always considering that this is the boundary corresponding to huge acceleration, and all the other lines are saying that we have a range of possible solutions that is not any on this plot. So let's
Professore, scusi, potrebbe ripetere il significato di queste linee gialle che ha disegnato?
Sì, le linee gialle che ho disegnato sono linee corrispondenti, ciascuna a un valore di AS su G0. 2, 4 e 6 corrispondono a dei diversi valori dell'accelerazione finale su G0. So we have to consider that we have another boundary. We have not only the boundary coming from the minimum acceleration for liftoff, but we may have also a limit on the maximum acceleration the vehicle or the payload can withstand. It means that we have to also to take this into consideration, and it's important in this plot also to keep in mind this, to make evident that if you consider, for instance, you need to get this delta V, and you take the minimum acceleration here to lift off. Consider that in this case you have also a high, because of the high value of V, it means of the propeller mass fraction, means that you will have a high acceleration at burnout. That means that probably if you have a maximum allowable acceleration for your payload, for instance, let's consider as an example this 6, it means that we cannot go towards, let's say, in the region above this line. And so, for instance, we have that our best solution here could be to take this point here that corresponds to a given value of T and of the initial acceleration. And here we are taking also into account, of course, this role of T. So this is the reason why this line is not monotonic, but we have a maximum, because we consider also the time we are flying, in this case, vertically. I didn't mention this, but of course we are flying vertically because we have sine theta equal to 0, equal to 1. Okay. Question? This part here, because we have, in this region we can play with different acceleration. And of course, at each combination of initial and final acceleration, and so the mass ratio will correspond also different value of the final delta V you realize, and of the needed propulsive delta V, which is directly related, of course, to the value of the propeller mass fraction. So, just a comment again on trust. It is not something that we desire to be as high as possible. It's not something that we desire to be as low as possible. It comes from constraints. We need that given value of trust, it's a requirement. We cannot go beyond the given level of trust. It's also a requirement that comes from failure. So this is just to say, if we like to improve performance, if someone says, yes, an improvement of performance is to increase trust. Right. you squeeze yourself, increasing thrust too much. So trust is actually a requirement, it's our goal, and should be to respond to what is required by the mission. So how much are these losses? We make two examples, comments on two examples, which are related to launchers and to transfer, orbit transfer. If we consider launchers, it's the only case you have to take into account also drag losses. It's not typically the case for in-space maneuvers. And if we look to launchers, but the gravity and drag losses are reduced by short burning times, and so it seems that we have to go as fast as possible through the atmosphere, but of course we have the penalty of having high speed. So what we can imagine that is let's say a trade-off solution if you like to reach this orbit from Earth is to fly vertically to minimize the time spent in the atmosphere, and as soon as we are outside of the atmosphere, we have the highest penalty here because we are flying vertically in terms of gravity losses at the highest penalty. So we try to reduce drag losses, but we have to pay for gravity losses. And then we try to keep a trajectory that once we are outside of the atmosphere, we try to minimize the angle between the thrust and the gravity force. We try to get theta equal to 0. So with this, of course, ideally, if you have no atmosphere, probably I would make an impulsive maneuver here and trying to make an Hohmann transfer from a point, an elliptic orbit from this point up to the. So in practically, you have to get orbit here more or less at this point. An instant maneuver. I remove Earth. I put all the Earth in a point, and they can orbit at 6,300 kilometers from the center of Earth. And this is the minimum orbit that we can imagine in the absence of the atmosphere. Of course, if you have this atmosphere, you have to go out of the atmosphere to get an orbit without losses. And so we can see that with a trajectory of this kind, we can make, let's say, a gross evaluation of gravity losses, considering that more or less the flight through the atmosphere will last, the vertical part of the flight would last about a couple of minutes. If you consider 120 seconds and you consider the gravity force, the acceleration of sea level is more or less 10 meters per second square, you multiply and you have that your delta V, with this cross calculation, would be about 1200 meters per second. The drag losses are more complicated to evaluate because it depends on the size of the rotor. But this means if you have a vertical trajectory lasting 2 minutes, you have this penalty. Just to have a basic figure. Then consider that I'll not go to an important subject that is called the launcher, let's say, final performance is based, of course, on the trajectory optimization, which is an art, is part of the course, I think, of spaceflight mechanics, there is also a special code for that, which is launcher flight mechanics, exactly because then you try to improve to get your best trajectory, considering all these kind of aspects, of course, in detail. So you try to optimize the velocity with the trajectory that to have a minimum drag losses or gravity losses combined with each other. And this can be achieved by suitable techniques. And would benefit also, in general, of the possibility to throttle your engine, to change its thrust during operation. Not always the case, or they cannot be easily controlled. So to get orbit, we have to consider the minimum orbit that would be at 0 altitude, and in this case it would be an expression that you know for sure of this kind with this gravitational parameter, which is the one for Earth, that is about 410 to the 6 kilometers cube second squared. So based on this and on the Earth radius and rotational speed, we see that at the best, if we consider launching at the equator exactly in the direction of rotation of Earth, we have that minimum delta V needed to get orbit, that would be 7.9 minus 146 kilometers per second. So this is the minimum ideal value we need to get any orbit around Earth. This is at 0 altitude. So, as I mentioned before, if we remove Earth, we have a point, mass point at the center of Earth, and we can orbit at this distance of from the center of Earth. We just have to provide enough velocity to stay in orbit, and this is what comes from flight mechanics. So to this quantity, we have to add, I believe, something like this, which are lossless, and we have also to consider speeding and gravity and aerodynamic losses. We can make a breakdown of delta V and consider that in general, so this was an example, but in general, we can consider that these losses are within 1.1 and 1.6 kilometers per second. These are gravity losses. Drag losses are between 50 and 200 meters per second. And for steering losses are also important in the range of 400 meters per second. So overall, you see that the gravity losses are the most important, and overall we have that delta V losses summing up is about 1.3, 1.8 kilometers per second. So with this we say that for a launcher to reach the orbit, we start from 7.9 because we don't always exploit at speed, depends on the orbit you are going to reach. you have to add something like this, and we reach values of what our rocket has to provide, our propulsion system has to provide, is more or less 9.2, 9.7 kilometers per second. And so this number is important. In a minute we will recall why this is important. In general, we make reference to 9.5 kilometers per second. If you are considering now the other example, that means maneuvering in space, we have that this curve not certain, so we can try to minimize gravity losses through short times and thrust provided in the direction of velocity. What happens is that this is not always possible, because if we consider an ideal impulsive maneuver, it's okay, have no gravity losses, not steering losses, but in the real world, impulsive maneuver means infinite acceleration. And again, we have to consider that we have constraints in terms of the acceleration we can reach. And so there will be an arc of the orbit to which we are increasing our velocity. And so even if we start from a circular orbit, we pass from, during this operation of the engine, we pass from this circular orbit to an elliptic orbit. And at this point, we have no longer the fact that the velocity is perpendicular to the gravitational force, and so we have some theta difference from 0, and we have some gravitational losses. So if we are considering a finite arc, a finite time for the operation, is not 0 time, there will be some gravitational losses. And these from tell us that to minimize the propulsive delta V, you should go make maneuver as short as possible. So even, for instance, you can also repeat, you make a small delta V at each G passage. But in any case, you have to reduce at minimum to avoid having high gravitational, high gravity loss. On the other example is that of having a very low thrust. This happens with electric thruster. And what happens if you have very low thrust? It means that the thrust actually is very long. It's many orbits. So you have huge gravity losses that can make your delta V provided propulsion system twice, even twice or more, the delta V that would be required by an impulsive maneuver. So the delta V required in low thrust maneuver will be far greater than what we can get by an impulsive maneuver. I think that we can go, if you like, we make a 5-minute break, not more than 5 minutes, because we are late. So just up to 13:15.
Professore,
Prego.
No, volevo comunicarle che insomma ci sta un rumore di fondo molto forte. Non è che si potrebbe cambiare il dispositivo con cui lei, insomma, cioè cambiare microfono, usare il telefono, perché è veramente, cioè, è molto forte.
Non lo so,
Eh,
perché se ne vanno altri 10 minuti se devo fare la connessione al telefono, potrebbe essere molto lunga.
ok. No, perché cioè, è veramente molto 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 forte. Cioè, è quasi rende inseguibile la lezione.
Cambia qualcosa così?
Io comunque dalle cuffie per un attimo ora va a ondeggia.
Così?
No, ci sta ancora. No. C'è un rumore.
No, perché se è un caso isolato,
Eh, sì, professore, cioè nel senso ora probabilmente il microfono che usa non so bene, perché con gli altri professori probabilmente usando il microfono diretto del computer, che loro usano le tavolette, quindi non c'è questo problema qua. Però in particolare nelle sue lezioni si sente questo forte rumore.
va bene, poi me ne sentirò anche, mi sentirò la registrazione così verifico com'è.
Ok. No, perché in caso.
Adesso è cambiato qualcosa oppure no? Perché
No, io, professore, la sento sempre con questo forte rumore di sottofondo. È come se ci. Sì, è proprio rumore classico. Poi continuo su.
un'altra persona, perché se me lo dice solo lei,
No, no, io sono buon uomo, il
Sono buon uomo, il
rappresentante.
rappresentante.
Quindi sto facendo carico di, di questo.
Prof, si sente molto male da tutta la lezione. Infatti, per quello le chiedevamo se magari fosse possibile utilizzare il dispositivo che avevo utilizzato ieri, che ieri si sentiva benissimo. Non so se può, non so se le richiede troppo, però sarebbe utile perché è veramente difficile seguire.
quindi sì, va bene, facciamo così. Tanto passiamo le giornate a giocare così. Così mi sentite? Sempre lo stesso rumore?
Sempre uguale, professore, si sente ancora.
Sì, professore, si sente costantemente questo rumore. Appena riprende lei la voce nel Teams, si sente.
Sentite?
Provi a riparlare, professore?
Sentite adesso?
Il rumore è sparito, ora però la sento un po' più basso. Io ora provo anche a alzare il volume del mio. Riprovi?
Mi sentite?
Eh, Non c'è più rumore, però lei è un po' più ovattato, almeno io da casa la sento così.
Sì,
Sì,
ma
anche
che
io.
non posso fare altro, questo è quello di ieri,
No, no, ma infatti ora si sente decisamente, ecco, ora sento decisamente meglio.
Ok, speriamo che tiene il cellulare, che non perda la rete. Adesso io mi sollego però.
Grazie, professore.
Così si sente. Ok.
Ora non ci sta più il rumore di fondo che era molto forte.
Voi mi sentite? Dico a quelli presenti qui in aula, perché adesso loro stanno senza microfono. Vi ricordate di che stiamo parlando? So we have at this point to make going back to launcher, because we have seen from the previous example that we need, let's say, a delta V. Let's take this as a reference, 9 kilometers per second, we are optimistic. So if we take the propulsion equation, the rocket equation, we see that if we assume specific impulse of about 300, 400 seconds, roughly, we see that this corresponds with delta V and this. And with these two quantities, it means that the mass ratio should be in the range between 8 and 20, depending on the value of the specific impulse. That means that the mass ratio should be in the range of 5 to 12%. So it means that the final mass should be between 5 and 10% of the initial one. So you see that it's to be evident how much propellant we have on board. And well, we have at this point also to make appear in this in our expression also our epsilon. We recall that delta V can be also expressed in terms of epsilon plus 1 minus epsilon lambda. And we see that we can, considering this expression, this is the mass ratio. And of course, let's say the limiting case is the one where we have zero payload. We have to consider that the final mass we recall it is the payload mass plus our inert mass. And altogether, this makes 5 to 12% of the rocket. It means that if we have that this quantity must be more than 0, it means that our inert mass should be less than 5-12% of the overall, of the initial mass of the rocket mass. So actually, if I put lambda equal to 0 here, we have that directly in the limiting case, lambda equal to 0 implies that the mass ratio is equal to our epsilon. So considering that the sinus mass ratio these values, we are in the limit of the technological capability of today. So the limits of technology will allow us to bring nothing in orbit. So this is why. So these are just these figures that tell us that we need to resort to multi-stage rockets. If we were on Mars, the escape velocity should be, I think, more or less 5 kilometers per second. In principle, we can also more easily realize a launcher with a single stage. The same is true for the moon. If you like to have escape velocity from the moon, I don't know, it's 3 or 4 kilometers per second. So it comes from these two numbers, the needed velocity to reach the orbit, the typical features of our rocket, and our limit on the inert masses. These are the figures on which we have to focus to justify multi-stage. In fact, considering different stages is something that allow us to achieve what cannot be achieved with a single stage. And this is done by dropping, by discarding what is no longer needed. What we do is that instead of once we have used part of the rocket which contains part of a given point, we don't need this empty tank, for instance, and so we discard it so that we have to accelerate less mass in this next phase. In principle, this would allow to reach any delta V. This is not exactly so, but in principle, this should be. Because if we consider that if we don't have this inert mass, if we have epsilon equal to 0, so ideally the propellant is self-contained, not extra mass, we could realize any delta V. Because from this equation, it would be just delta V equal minus QEQ logarithm of lambda, and lambda is just, of course, is E minus delta V QEQ, and so we have just something like this. It is asymptotically less and less the value of lambda, but always we can have a positive lambda. The fact that we have our epsilon that occupies room that else will be left to the payload does not allow to reach any delta V, and so we have to resort to multi-stage, and that can also help us for other reasons, because we can optimize our thrust level and our specific impulse to different range of operation. For instance, I mentioned before the limit on the acceleration. If we have a single stage, this is a very important problem. If you have a multi-stage, you can consider a thrust level for the first stage and then a lower thrust level for the next stage, so that you can manage the different masses and the different acceleration that result. If you have a single stage, you have to consider that you are consuming propellant, and if you have a mass ratio, as we mentioned before, of 10, let's say, or 10%, you have that your acceleration, your final acceleration will be 10 times the initial one. If you have different stages, you can restart from the next stage from a lower thrust level that allow you to manage the acceleration level, and for each stage you will have a mass ratio of a propellant mass fraction that will be a propellant mass fraction that will be not so large as for a single stage. So what is the meaning of this statement talking about multi-stage rockets? We define a stage as a complete propulsive unit which is part of what we will call sub-rocket. So we define, in general, our rocket as made of different parts we have here, this will be the payload, and we have here, for example, 3 different stages. First stage, second stage, third stage. These are 3 different parts that will be discarded. One, of course, also here we will have some engine behind, hidden behind the lower stage. So overall, we have that this will be the initial mass of the rocket, and we can consider that for the first stage, we have this as its payload. So for the first stage, has to achieve given delta V, which is obtained, which is provided to all these parts that is made by the second test stage and payload. That is the payload for that stage. So this is the first sub-rocket. When we have here the propellant and the inert mass fraction of this first sub-rocket. So to see it this way, we can move to the second sub-rocket at this point when we complete the operation of the first sub-rocket. We have consumed all, and we have left this MS1 that we no longer needed. We don't want to accelerate it, so we discard it. At this point, what is left it just was the former payload, mu1, which is the initial mass of the second sub-rocket. At this point, for this, we can identify again this mass, which is ms2 plus mp2, where we have the inert mass and the propellant mass for the second rocket. The third stage and the payload for this sub-rocket. Finally, we have the third sub-rocket, whose payload is the real payload here. And then we can define again the propellant of the third stage plus the inert mass for the third stage. And this overall would be the payload of the second subrocket will be the initial mass of the third one. So this is an example of a three-stage rocket. We can generalize this kind of definitions for 2 stages, for 3 stages, for many stages. So the subrocket 1 is the complete launcher and or rocket in general, and the subrocket 2 is the whole launcher minus the first stage, and subrocket will be subrocket 2 minus the stage 2, and in general the I+1 subrocket will be the I subrockets minus the I stage. So to analyze this multi-stage rocket, of course we can define for each subrocket the different, and so we can define. Let's move here. We have a mass ratio of the generic subrocket will be the final over the initial mass of this subrocket. We can define a payload fraction, propellant fraction for the subrocket. A payload fraction for the same subrocket, mu I over m0I, and also a inert mass fraction, msi over msi plus mpi. The usual rules hold, so that we have Zi plus mri is equal to 1, and we can then we can express the inert mass fraction as a function of the propellant. Sorry, the inert mass as a function of the propellant mass in this way, and also MSI plus MPI as 1 over minus epsilon I MPI. So we can take our previous relation. Among them, we have seen also that we have from this one, M0, mu, I plus MSI plus MPI, dividing everything by M0, I have that 1 is equal to lambda plus Z1 minus epsilon, and from which we have also the relation that Z is 1 minus minus epsilon 1 minus lambda. And also that MR is equal to epsilon plus 1 minus epsilon lambda. So these are the same relation we have seen for the single rocket. We just put a y subscript to emphasize that we are talking about a subrocket now. And the spatial aspect is the fact that now what happens is that the payload of a subrocket is the initial mass of the next subrocket. So we have that the actual payload mass is the payload mass of the last subrocket, but we have that in general the payload mass of a given subrocket is the initial mass of the next one. And we can reach at a given point the of course there will be that mu1 is equal to m02, and also we can say that m0 is equal to m01. For the first subrocket we have that the initial mass is exactly the overall rocket mass. So we are interested to this quantity. To the payload mass, and of course starting with a given initial mass. So we can identify now the quantities that represent the whole rocket and not only the single subrockets. And we can for sure identify our lambda, that will be also in this case mu over m0. How this payload mass fraction is related to the subrocket mass fractions is easy. This will be also mu n. I can divide by m, and this will also be the initial mass of the last subrocket will be also the mass of the n1 rocket. So these are equal. I can divide by the initial mass, that will be the payload of the former subrocket, and I go ahead up to reach our m01, mu1. So we proceed and we see that here our lambda is lambda n minus 1, lambda, better not here, lambda n minus 2, lambda 2, lambda 1. So we can, it's well known that for multi-stage launchers considered in with stages in series, so in a tandem configuration, we have that lambda is equal to the product I equal 1 to n of the lambda I. So the final payload ratio is the payload to each stage. We can also see the other quantity, and I need room, so I move to the next page. We can define a Z for the whole rocket, which will be MP over M0. And of course, M0 is M0, and MP will be the sum of MPI and this point is it can be convenient. Consider MPI for each I can divide multiply by M0 I, so that we make appear our Z. This is the propellant mass fraction for each stage that must be multiplied by this M0I over M0. So the initial mass of the generic, and we have to sum for each value of this index I. So we see that, for instance, if I consider I equal to 1, I will have here Z1 plus M01, M01 over M0 is 1. Then I'll have plus Z2, and then I have here M02 over M01, which is lambda 1. Plus Z3, multiplies M03 over M01. I can write this in this way. And so you have that this is lambda 1, this is lambda 2. And so on. So at the end, I can write this in a more compact way. I have to consider the product of all lambdas minus the last one. So I will write this in this way. Z is equal to Z1 plus, I consider now the sum equal to 2 up to n of Zi product, and j equal to 1 I minus 1 lambda j. And this is for the propellant mass fraction, which is related to propellant mass fraction of each stages, but also to the payload fraction of different stages. And the payload fraction is also related to the inert mass fraction, epsilon, that will be ms over ms plus mp. And so we have to sum the inert and the propellant masses. We can, this is the definition, we can make a first recasting of this whole rocket terms dividing by the initial mass, because I can also write this as ms over m0 divided by ms plus mp m0. I think this making appear payload ratio can at least simplify the denoting appear here the overall lambda. So you see here I have this m0 minus mu over m0 is 1 minus lambda, and ms over 0 is given explicitly under the summation. And here we can exploit the fact that MSI is epsilon 1 minus epsilon MP, and so we can now look in more detail to this summation. Where we have here now MPI over M0. MPI over M0 will be MPI over M0I, M0I over M0. So we recognize this term exactly as we have seen for the propellant mass fraction. It will be the product of different value of lambda up to the stage I minus 1, and this will be our Z. So 1 minus lambda, and you have the product here for J equal 1 to I minus 1 of lambda J. Now we have epsilon and Z. We know that there is a relation between Z lambda and epsilon. We have seen it before, and in particular we know that Z over 1 minus epsilon is equal to 1 minus lambda, and so we can express now epsilon as a function of the epsilon of each subrocket by a function of this epsilon I and of lambda of the different subrockets. So with this, I just make this substitution, And the result is that epsilon is 1 over 1 minus lambda that multiplies epsilon 1 minus lambda 1 plus sum I equal to 12 of epsilon I 1 minus lambda I, and now product j equal 1 to I minus 1 of lambda j. Okay, so this is, we have seen the expressions of the different quantities, in particular of lambda and epsilon, as a function of the epsilon and lambda of each subrocket. At this point, we have to go back and see and go back to the reasons why we did definition, what we have to do with this. So what we have to do with this is to get a given delta V, and possibly we would like to get this delta V with the maximum value of overall lambda. So our delta V that we will realize with our multi-step or multi-stage rocket will be obviously the sum of the delta V provided by each rocket, each sub-rocket. So this is rather straightforward. And also, we know how rockets work, at least from the rocket equation. And so this delta Vi will be the delta V provided by each sub-rocket as a function of epsilon and lambda and specific impulse of that rocket. So our delta Vi as the usual expression, where we can make appear the quantity that will. So our delta V will be the sum 1 to n UQ I and logarithm of epsilon I plus 1 minus epsilon lambda. So this will be the results obtained by our multi-stage rocket. And we can see that in this way, we can realize we have seen by reasoning, a higher delta for a given lambda, for a given overall lambda, or the same delta V with a higher lambda. So at the end, what we like to see is how we have to divide this in different subrockets. I'm aware that you already know this by probably by the other courses, but we will see it again to make our comments. And what we do here is that we would like to maximize our lambda for a given delta V, and we see that this is equivalent, so max and given, and this is equivalent to consider the given lambda with the maximum that allow to get the maximum delta V. So how we do this? We look for a simple problem by Lagrange multipliers that allow us to get the constrained maximum, and in practice what we have to call that if we are considering this problem here, this will be our constraint. What we have written here is something is a known value, and we try to maximize to express the other relation that we have is that lambda is equal to the product of lambda I. So we have these two relations available, and we can try to find this quantity this relation valid, or do the opposite, exchange them. So we can try to keep these and maximize this one. What is done, usually consider, I just write this and I will end. We consider a function of the parallel mass function of different stages. It will be but it's convenient to write this in a logarithm form because it becomes a summation. So instead of saying the products, we have a relation, it's equivalent, and so we can maximize this other expression, or can keep it as the constraint. Actually, what we can do is to consider that we have here this must be, well, already of lambda, that should be maximized plus Lagrange multiplier delta V sum delta VI. So this is Lagrange multiplier. We have to maximize this function. This will be a function of lambda, and also this one is a function of lambda I. So we make a derivative, we find the maximum for this expression. So this is the augmented function through this Lagrange multiplier. Considering here delta V, consider as a function of lambda I this time, plus beta minus sum. So in the first case, this is a constant given, this term here. In the second case, the constant is this one. But we see that the result is this. And let's stop here today. Spero che la parte, insomma, questa seconda parte sia sentita bene.
Sicuramente meglio della prima, professore.